Let's get started. Welcome to the third unit of the course, which is about storage. And not only is it about storage, it also switches the hidden hero of the course. In units 1 and 2, the hidden hero is the compiler. We're continually looking at some code and seeing that the compiler is doing something really interesting with that code. For instance, maybe the compiler is automatically changing a recursive function into a loop so that it runs faster. So although you're learning a lot about the way data representation works, about the way instructions work, you're also learning about how cool compilers are. For the rest of the course, we're kind of learning about how cool operating systems are. So what we're going to talk about today include sort of like an initial picture of how the innards of an operating system work, as how your problem set 3 will work. But we're going to start out with a look at the trends in hardware technology as they relate to data storage. In particular, we're going to look at cost, because cost is one of the more amazing changes in that over time. So hopefully you guys enjoyed problem set 2. Problem set 3 is out now. We have a midterm next Thursday. The midterm will be in Emerson 105. It will not be here. So Emerson 105 is big enough that everybody can fit with space next to them. Our midterms are Open Book, Open Note, and Open Computer. You are allowed to look at stuff that is directly linked off the 2017 wiki, and that's it. So you can go to 2017 and look at our lecture notes. You don't need to print them out. If it's easier for you to look at them, you can print them out, of course. You can go to sites that we link to directly, but it's probably not a good idea for you to go through a Wikipedia click festival and end up being amazed at some picture of a cat. That's against our policy, and it also is a waste of your time. No Stack Overflow, obviously, I hope. Any questions about the impending midterm? Yes, name?
So Noah,
Noah.
You mentioned we can use anything that's linked on the site. Does that mean we can use GitHub repos that are CS61, so section and lecture material?
Yeah. I think we generally ask you not to run compilers.
Okay.
Right. We also generally try to ask questions so that running a compiler wouldn't really help. But we ask you not to run compilers, assemblers, etc. But you can look at code. Yes?
All written, we turn in a paper.
So what we have typically done, and I recommend that everybody bring their laptop. What we did last year and the year before is people actually typed in their answers and submitted them to a GitHub repository. 90% we're going to do it the same way this year. Question?
Is it valid to use resources not linked by the course site, but linked by an instructor on Piazza? I know there was a
We're going to turn off Piazza before class. So if you want something that's linked off of Piazza, you have to print it out. Right? There is a sort of an open note thing. Other questions? Patrick?
Will there be a practice midterm?
Yes, we're going to release a question bank. That will probably be out today, tomorrow. Okay. So the first thing we're going to talk about is essentially all of the different storage technologies that go into a typical computer, like your laptop, like the grading server. And although this term is not a fabulous term, we call this, everybody calls this, the storage hierarchy. What hierarchy generally means is that there's one thing that completely subsumes another, that completely subsumes another, that completely subsumes another. That's not strictly speaking true of the storage hierarchy. You can have things in one level of the storage hierarchy that never make their way down to the lower levels. But that's okay. We'll put up with it. So the storage hierarchy is drawn like this pyramid. And we have two directions that you can think about. As we go up the pyramid, things get faster. and they get smaller, and they get super expensive. And as you go down the pyramid, things get slower, but they also get bigger, and they get very inexpensive. Okay, what's at the top of the pyramid? Registers. Yep. Now, roughly how big are registers? Anybody know? How much data can you fit in a typical x86 64 machine's registers? Just ballpark it. I don't actually know the precise answer. There's a 64 bytes per, so somebody said kilobyte, which would be my guesstimate. There's 64 bytes per register. There's at least 16 registers that we know about. In fact, there's a bunch of other registers storing floating point data and a bunch of other registers that are sort of storing magical data that you can read about in the book under topics on vectorization. So I think about a kilobyte is right. So we're going to write our sizes in megabytes. So this is 0.001 megabytes worth of registers. As we work down the pyramid, well, just name some other storage technologies. Cache. So in modern computers, there's actually multiple levels of cache. We have the L1 cache, we have the L2 cache, we have the L3 cache, and on some computers you'll have L4 caches. And what these caches are doing is the smaller ones are closer to the processor. You can think of the processor as sitting like the high priestess at the top of this pyramid, like waiting for the data to be delivered to her. So the level 1 cache is the closest cache to the processor, and so accessing it is the cheapest. The level 2 cache, the level 3 cache, these are a little farther away, but they're bigger. Okay? So they're less fast to access, but they're larger, which is good. So some typical numbers, and this is taken from specs for an iMac, like the one that I have on my desk. Every processor on my iMac has its own level 1 cache. My iMac has 4 processors. So they each have their own level 1 cache. And those are 32 kilobytes big. Then the level 2 and level 3 caches are shared. So a level 2 cache might be shared by 2 processing units, whereas the level 3 cache is shared by all of the processing units. Okay? And the level 3 cache on, again, this is just one machine, so these are just sample numbers, is like 1 megabyte. And did I write it down? Of course, I wrote it down and threw it away, but I believe that the level 2 cache was 256 kilobytes. More storage technologies. Disk. How many kinds of disk are there? So I could just keep going. You guys are, despite being millennials, you guys have heard of hard disks, yes? Okay. So this is sort of the older technology for storing information in what we call a stable way. Okay, I'll define that in a second. So the newer technology is flash memory and solid state drives, right? And so why don't we put hard disk here and flash SSD here. What goes in between? There's one missing slot. RAM. So DRAM. So we call this DRAM sometimes when we decide to be pedantic, because everything above this line is also random access memory, but it uses a different, more expensive technology. So about how big is DRAM?
8 gigs.
Like 8 gigs, roughly. So, and I'm not multiplying by the true factor here, right? So I'm playing some games with powers of 10 versus powers of 2. Sorry. Roughly 8,000 megabytes. About how big is a typical flash or SSD? Like 256 gigabytes, 512 gigabytes. If you really got money, you might get a terabyte. And on a hard disk nowadays, you're probably going to get at least 2 or 4 terabytes. Okay? So how many orders of magnitude have we got in size between our smallest storage and our largest storage? Like 10 to the 9. There's a 10 to the 9 difference in these sizes. Okay? Let that sink in for a minute. Think about other things that are 10 to the 9. There aren't very many things in our lives that are 10 to the 9. It is amazing to me when I bother to think about it that all of the computation on my computer is happening up here at something that's 10 to the 9 smaller than what I think of my computer as containing, which is basically the contents of the disk. Enrique.
So you said it's a matter of money mainly. So let's
Yes, we'll talk about money in a minute.
Can I answer my question?
Yes, you can. I'm sorry.
Amazon wants to provide super powerful computers only with cache registers and RAM because they want to put a lot of money into these powerful computers such that people will pay for it. Is that possible?
Okay, so the question was basically like, if you wanted the most super powerful computer you could build, would you just give it cache? So that it had like 4 gigabytes or 8 gigabytes of cache memory. Okay, so cache does mean multiple things here. So if you spell it with an SH, you're probably talking about billions of dollars for such a computer. The other problem is a physical problem, right? So if you think about it, memory takes physical space. And physical space is limited. The further you are from the processor, the more wire information needs to travel before it reaches the processor and can be processed. Okay? That information travels at roughly the speed of light, but given the speeds that your processor is working, speed of light matters. So where are you going to put those 8 gigabytes of cache? You could imagine a sort of a solid sphere that's encasing of cache memory, that's like encasing the processor. And at that point, like the heat that the processor generates may not be able to get out. Like there's all kinds of fantasy weird problems that you get with this architecture. But the main problem that you get is just too expensive. Okay, the amazing thing is that the processor designers and us as software designers have developed a number of like cool performance strategies that help us basically get pretty good performance even despite this 10 to the 9 difference in size. Okay, question, sorry, name? Alex.
What's the difference in speed then between like a hard disk and a register?
It's a great question. What's the difference in speed between a hard disk and a register? So speed we can measure 2 ways. We can measure it in terms of latency, and we can measure it in terms of throughput. So these might or might not be terms that you guys have heard before. So latency is measured in units of time. So it might be a unit of seconds. And this is the amount of time it takes to gain access to a piece of data. Okay? Then there is throughput. This is the other way that we measure the speed of storage. And throughput is measured in units of bytes per second. Or, you know, multiples of that, so megabytes per second. And this is how fast you can transfer data once the data transfer is going. So this is a delay. And this is a speed. So this is the speed of transferring data. The interesting thing about latency and throughput is that they aren't linked. Okay, so let me give you an example. We'll look at some concrete examples of latency and throughput on accessing disks in a couple minutes, probably in the second half of the lecture. But a famous example is let's say that you want 1 byte of data, or 1 web page's worth of data, and you want to upload that to Amazon. How would you do that? Amazon has APIs. You just sort of use the network to transfer that data. Now let's say that you have a hard drive's worth of data that you want to transfer to Amazon. How would you do that? You could use the network to do that, but the network has a very low throughput. So what Amazon offers is they offer a service where you can mail them a hard disk. You mail them a hard disk, and they just sort of plug it in to your machine. There are different sort of joke names for this. One of them is SneakerNet, because you're carrying a disk from one place to another. Another is 101Net, because the image is of people driving up and down Route 101 in San Francisco with disks in the back of their car. So 101Net, SneakerNet, US Postal Service, these have very high latency, because it might take 3 days for your disk to get there. But it has very high throughput, because the disk that you're sending has 4 terabytes of data on it, right? So 4 terabytes over 4 days, 1 terabyte a day. That's a very large, that might be larger than the internet can support, depending on where you are. Okay? For a more down-to-earth example, right? If you have one question, you might call the reference librarian and ask the reference librarian your question. But if you want to learn a lot of information, you go to the library and you take out the book. Taking out the book has a longer latency than calling the reference librarian, but it has higher throughput to read than to talk to somebody a lot of the time. Okay, so we have a technical example, a dumb example. Is everybody relatively clear on these concepts? Great. We'll get to the throughput of some of these technologies a little later. Let's just talk about speed. Anybody got a guess for the, so by speed, I mean latency? Anybody got a guess for how long it takes to access a register? Patrick?
On the order of picoseconds?
On the order of picoseconds. That's too small. Okay, so here's a way that you can ballpark it. What's the speed of your laptop's CPU? Roughly. 2.4 gigahertz. So that means it can do 2.4 billion things a second. It can do up to 2.4 billion things a second. An example of a thing is adding 2 numbers together that are both in registers, right? So roughly, if we take the inverse of 2.4 billion, we'll get how long it is to access a register, right? So that is, rather than 2.4 times 10 to the 9, it's 1 over 2 times 10 to the minus 9, roughly. I'm sure I screwed that up. What we end up with is a number that's measured in the small numbers of nanoseconds. Picoseconds, I think, is 1 million times smaller than that. So what I've got here is 0.3 nanoseconds to access something that's in a register. 1.1 nanoseconds to access something that's in the level 1 cache. 3.3 nanoseconds to access something that's in the level 2 cache. Maybe 12.8 to access something that's in the level 3 cache. Once we get out to main memory, things really start slowing down. Roughly 63 nanoseconds to access something in main memory, also called primary memory. Okay, any guesses for the relative for the latency of accessing something in a SSD or in a cache, or in a hard drive? Yeah, Rob. For an SSD, maybe half a millisecond. Anybody have any way of like ballparking this? That's about what I've got. I've got 0.1 milliseconds for Flash. Flash has been improving in terms of speed quite quickly. In terms of disk, this is a different situation altogether. If your disk is not already spinning, if your disk is idle, and you start reading a byte from the disk. Okay, how many people know roughly how disk technology works? Okay, so about half the class. That's good. One of the interesting things about disks is that disks are literally round. A disk is the underlying technology of a disk is a very thin platter with magnetic material on it that spins really, really fast. It spins 7,200 revolutions per minute, roughly. So it's going completely around like 120 times a second, which is pretty fast. And there's a head that's hovering over the disk with like, just the tiniest little distance. And that head can detect whether the polarity of the data on that disk head is like up or down. And that's how bits are encoded on the disk. So for energy reasons, keeping that disk spinning, once you actually get it going, it's not that expensive, but keeping a disk spinning is one of the more energy expensive things you can do on a computer. And it also increases the likelihood that something is going to break, right? So like one of the reasons why our laptops all have SSDs now, aside from the fact that they're faster, is that if you drop a spinning disk, it can literally break, or it can like sort of scrape against the head. These are, the way people make disk drives now is much more reliable. You don't like just jostle it and have a problem. But still, these are mechanical devices. So basically, when the computer is idle, the spinning disk gradually comes to a halt. And when you want to read a byte, it's got to spin itself up to 120 revolutions per second. And then the head has got to get to the right place on the disk to find the data that you need. All of that takes a long time. It takes roughly 9 milliseconds. Okay, so we have a factor of 100 here. We have a factor of a lot more than 100 from the top to the bottom. Is it a factor of 10 to the 9? Sorry, question.
Is that 9 milliseconds a figure from rest or from the disk is spinning?
That is from rest. So hard disks are a situation where throughput can be quite high, even though latency from rest is also high. So it's slow to access your first byte, but once you've accessed your first byte, that disk is spinning. And the other bytes that you need are just sort of like just waiting for you. They're traveling underneath the head at a speed of 120 revolutions per second. Okay? So if we switch to throughput numbers rather than latency numbers, you'll find that the sustained throughput of Flash, like this is a difference of a factor of 100, but the throughput of a spinning disk is really only, it's slower than an SSD, but only by about a factor of 4. On modern Flash, we'll often see numbers that are like 500 megabytes a second throughput for the disk, and for the SSD for the SSD or the Flash, and for a hard disk, more like 156 megabytes per second. Okay, so a factor of roughly 3.5, 4, rather than a factor of 100. Disks are bad at accessing the first byte, but if you read the following bytes, disks are not that bad. This is one of the reasons why they're still in use. Okay, so we have a factor of 10 to the 9 size difference. we have a factor of, I believe, like 10 to the 7 latency difference. If we want to look at some real big numbers, some huge numbers, we want to look at cost. And in particular, we want to look at cost over time. And this is the biggest number that we're going to look at in the course. So magnetic core memory, which was one of the earliest one of the earliest memory technologies, random access memory technologies, was invented in 1955. And had you been around in 1955, you could have bought a megabyte of memory. It is now 2017. And what I would like for us to do is to try and fill out this matrix, where this matrix is going to talk about costs. We're going to use constant 2010 dollars for memory, so DRAM, flash, and hard disk. So I'll get you started. And we're talking about dollars per megabyte. In 2017, hard disk costs for a megabyte of hard disk storage. I'm not going to ask you to guess, although it's fun to ask you to guess, but I think it is fun for you to have a number in your head. What do you think this number is going to be? How big or how small? Dollars per megabyte. The answer is 0.000022. Okay, so it's 22 millionths of a cent per megabyte hard disk storage in 2010 dollars. For flash, now you have ground to stay on. Okay, so flash, about how much more expensive do you think flash is going to be? You're right. It is 0.00023. I'll put another 0 there just so you can see that that's 10x more expensive, but still dirt cheap. Okay, memory. How much more expensive is memory going to be than flash? 50x. What's your guess?
I was going to go with 100x.
100x. I believe that it's just 10. .0049, so it's about 20x. Okay, so flash did not exist in 1955. Does anybody want to, like, guess these numbers? $30 and $5. That is too low. Okay, come on. Just call it out. Call it out. Yeah. $20 million. $20 million. That is too low. Meg, that's too low.
Okay, I'm out.
You're out. Yes. $2 billion is too high. Congratulations. Memory in 2010 dollars, okay, so it was less in absolute terms, per megabyte in 1955 cost $411 million. And I'll just put the same number of significant figures just so we go home. Hard disk cost $6,233 per megabyte. Okay? So if you look at this difference, so that difference is 18.6 times 10 to the 12. It's like 10 to the 13. Factor of 10 to the 13 cheaper now to store data on hard disk than it was to store data in memory in 1955, in constant dollars. So this is not accounting for inflation. Even this number, although it is less, it's still large. It's 10 to the 11, more or less, right? The 10 to the 11. That's 1955 to 2017. So if you look at these prices over time, you also get a sort of an interesting, strange look into how hardware technology is changing. The way that hardware technology is changing, unfortunately, those of us in software have to react to it. We don't get to control it. We get to occasionally work with people who are doing things. But Flash has gotten way cheaper. Just in 2003, Flash was more than 200 times more expensive than hard disk. And now it's only 10 times more expensive than hard disk. There are a number of people who think that eventually Flash will become cheaper than hard disk. Okay? So when we see a factor of 10 to the 9, in terms of size, we have to program around it. When we see a factor of 10 to the 7 in terms of latency, we have to program around it. When we see a factor of 10 times 11 in cost, that gives us a big incentive to program around it. Right? If all of these technologies were the same cost, then we would just, as Enrique suggested, we would just use as much cash as we could. But they are not. We cannot afford it. Okay, one more thing. Some of these storage classes are called stable, and some of them are not. And the boundary line is here. These are stable. And everything above that boundary line is unstable. What stable means is the data stays if you pull the plug. So the data does not need power to continue to exist. In unstable storage, when you pull the power, the data quickly degrades. It doesn't go to 0 immediately, which is a kind of a, maybe I'll try and look this up and send out a link to it. But people in the security community, the kind of people who you will learn about in James Mickens's CS263 course, are continually running science experiments to find out how naughty they can be. And one of them was they wanted to see if they could look at what the contents of a computer's memory after that computer had shut off. And all they do is they made the computer cold. And then the memory kind of kept its original data for much longer than anybody would have expected. They could read secret keys out of the memory long after the computer had been turned off. That's a fun preview of Mickens. But for this course, stable storage, the data stays after you pull the plug. Unstable storage, the data goes away after you pull the plug. So if there's a disaster, you lose your data, unless it has been written to stable storage. Okay? Question, Will?
Can you explain the difference between Flash and SSD?
I literally cannot. The question was, can I explain the difference between Flash and SSD? So Flash and SSD, these are both, SSD stands for solid state drives. These are both kinds of technology that use memory but manage to preserve their data after the plug is removed. They have some other similar characteristics. Hard drives last kind of indefinitely. No matter how much, not indefinitely, hard drives have a lifetime. But you can rewrite data over and over again on a hard drive with no consequence. Whereas on Flash and SSD, if you rewrite the same location on the drive too many times, that location on the drive goes dead forever. That said, I don't know what the difference is in the hardware. Where would you look to find out? Wikipedia. I didn't mean that to be taking you to school. It's just part of the thing of the course is knowing how to find these things out. CS146 is another good idea. Okay, let's take a break, and when we come back, we'll run some programs. In the storage 1 subdirectory of the lectures repository, you will see a lot of programs. All of the programs that start with R are programs that read data, and all of the programs that start with W are programs that write data. That is all they do. They read and write data in different ways, and what those programs will let us do is they'll let us sort of get a grip on the way that the storage hierarchy works, particularly across this boundary, the boundary between stable and unstable storage. We're also going to look more, definitely go to section as always, but in section we have some interesting programs and exercises that help you understand the consequences of storage from DRAM to cache. We'll look more at that on Thursday as well. But across this stable storage boundary, this is where the operating system gets involved. So here's how we draw an operating system. There's a line, and then there's a U above the line, and there's a K below the line. So let me explain further. So when we refer to an operating system, you think that the operating system is the programs that you run. But in this course, we spend a lot of time understanding the way that the programs that you run are coordinated. Every computer has privileged parts of its hardware. And those privileged parts of its hardware are managed by one program. And that program is called the kernel of the operating system. So when you have heard the phrase the Linux kernel, it's talking about the kernel of the Linux operating system. Every operating system has its own kernel. Mac OS has a kernel, iOS has a kernel, Windows has a kernel. And what the kernel is the software that runs with full privilege. What full privilege means is that the software, this kernel software, can actually manage the hardware that's attached to the computer. So if you want to read data from a disk, which we often will draw like this, for some reason we draw disks like this, even though most disks are SSDs now or flash, and they aren't actually cylindrical. But this is sort of like the typical picture of a disk. If you're a program that's running in user space, as every program that you run is running in user space. So for instance, if you are our W01, whatever program, you don't get direct access to the disk. If you did get direct access from the disk, that would be a risk. Direct access to the disk would allow this program to read everyone's data and to overwrite everyone's data. The disk is dumb. The disk just knows about bytes. The picture that you have of the disk is not dumb. The picture that you have of the disk involves a file system. There are files in /home/your-name. There are files in /temp. There are files in /bin. Some of those files you have permission to read and write. Others you don't. You can safely share, you can at least semi-safely share one file system between many users and use permissions so that the users can't overwrite each other's data or can't read data that shouldn't be read. All of those permissions are implemented by the kernel. So the kernel uses some part of the disk to store permissions and then enforces those permissions on requests from the user. But all of those requests would be meaningless if the user could just access the disks directly. That's why the user can't. So that is why the disk is below this line. So this boundary separates unprivileged code from the privileged kernel. So what kind of, what operation does the user program use to talk to the kernel? We've seen them already. That's what a system call is. So a system call is a function call that the user makes to the kernel. Okay? But unlike a normal function call, that system call involves calling out to a region of greater privilege. We'll see a lot more about that privilege control transfer in a later unit. For now, just know that a system call crosses this boundary. So we can call this the system call boundary. And a system call is far more expensive than a regular function call. The reason that a system call is far more expensive than a regular function call is that a system call is transferring from one zone of privilege into another. That essentially requires flipping a lot of switches in the room. Right? I mean, that was an analogy, so why do I say right after it? System calls are expensive. So it's the kernel's job to provide an interface, a system call interface, that is effective, that is efficient, and that is safe. And very few operating systems manage this. Linux, for example, doesn't. Oh well. Oh dear. So because I want sort of direct access to hardware for this portion of the lecture, I'm actually logging into the grading server, which is an Amazon machine hosted far away. We have a question here. If I rip the disk out of my friend's computer, could I read all their data? That depends on if their file system is encrypted. If they chose, when setting up their operating system, to encrypt their home directory, then no, you could not. If they did not choose to do that, then yes, you could. As we sort of get more security conscious, the defaults for questions like that are changing from being, I don't care about security, I just want it to run as fast as possible, to I care at least a little bit about security, so why don't you make it the default? So like if you stole my iPhone and you didn't have my thumb and you got 10 guesses wrong on on my passcode, then the iPhone would reset itself. But furthermore, the iPhone's data is all encrypted by the passcode. So even breaking into the data would not, even like just physically ripping out the memory would not necessarily help you. I am not saying that that iPhones are like perfect in terms of security. They're just better than most laptops. Okay, let's take a look at W01 sync byte. All of our programs work roughly the same way. So all of the programs that we're going to look at. What they differ, the way that they differ, is in how they write or read data to or from the disk. So let's look at the loop first, and then we'll go back to the start. So this is the central loop. So things to notice. We are not calling printf. We are calling this function instead, write. Write is a lower level function than printf. In fact, write is a system call. You can read about write by, you can read about write by typing woman write, but you have to often give a number. System calls are all documented in section 2 of the manual. So if you just type woman write, you will often get the wrong manual page. You'll get a manual page for some program called write. So you have to be more specific. You have to say, I want the system call write. That's what the 2 means. So you can read all about write's definition here. It's pretty simple. You can also read about it on the wiki, on our wiki. It's linked off the problem set. So write writes up to count bytes from the buffer pointed to by buff to the file referred to by the file descriptor FD. What's S size t as opposed to size t? That is a great question. S size t is the signed version of size t. So it's as big as a size t, but it can be negative. And the reason that these system calls return S size t is because all system calls might return an error. Almost all system, there are like, you know, there are a very small number of system calls that do not return, that do not potentially return an error. And system calls have a single way of returning an error to the user, which is that they return -1. Every system call that returns an error returns -1, and the WUM manual explains what those errors are in a section called errors. The way that the error return works is the system call returns -1, and it sets a sort of a weirdo global variable, it's gross, but it happens, called errno, E-R-R-N-O, and to one of these values. And these values sort of explain what could have gone wrong with the write. So write being one of the most basic system calls that we have, we can see that it can have all kinds of errors. We'll learn about some of these errors later in this unit. But here's an example one that actually makes makes direct sense to, if you read the definition of the error. So EFBIG, real compressed, right? Nerds don't want to type too many characters. FBIG. You get that error when you write too big a file. That is a different error than this, ENOSPIC, which means that the disk ran out of space. So one of these, the file was just too big. There was some file size limit that the operating system was imposing, and you went over it. In the other, the disk is out of space. This is a much more serious error, because generally, soon after your disk is out of space, your computer crashes. OK, so back to this loop. How many characters are we writing at a time? 1. That's the third argument to write. It's the number of characters that we're writing. And what we see here, after the write system call, we check for errors. And if there's an error, we exit. And then every now and then, we're going to print a report of how many bytes we've written so far, and also the speed. Now let's go up to the beginning. This is the line that we want to concentrate on. So here the open system call is how we open a file. We ask the operating system essentially for permission to work with a file. And the arguments for open are the file name and a bunch of flags. So what these flags say here is, I am only going to write this file. You should create this file if it doesn't exist. You should get rid of all of the data that's currently in the file. So you should truncate the file to 0. And you can read about all of these flags on the open manual page. And then this. This one says, operating system, this is a very important file. I want every write that gets made to this file to fully complete, beginning to end. I want it to make it onto the disk before you return. OK? So what that flag says is that every write to the file is going to make its way all the way from registers out through DRAM, down, in this case, to flash and back. Every single write. Let's run this file. Let's run this program and see how fast it is. Shouldn't it be r not equal to -1 rather than 1? No, this is correct. What the write system call returns is the number of bytes written. So in this case, when we write 1 byte, when we ask to write 1 byte, there are 3 possible return values. There's r equal to 1, which is what we want. There's r equal to -1, which indicates an error. And there's r equal to 0, which in this case will never happen. But if it did happen, would be confusing and bad. So the if statement says, I want you to have written exactly what I told you to write. When it gets passed from registers to hard disk, is it actually being written to all of the intermediate layers? Yes, it is. The reason is that the way that the hard disk knows what data to write is that it accesses that data from primary memory. So the data has to be written to primary memory before it makes its way to the disk. There are only some very advanced devices that don't follow that rule. OK, make. Have in your head how slow you think, you think this might be. Any guesses? Or how would you calculate? So remember, what's interesting about this program is this program, every single write is going all the way to the disk. So what would you invert to get a rough speed? The latency, right? The latency of the flash drive. This is running on a flash drive. So what's the inverse of 0.1 milliseconds? 10,000, right? That's 10 to the minus 4 seconds per byte. So invert that, and you get 10,000 bytes per second. If it's less than 10,000 bytes per second, either we're actually running on a slower technology, maybe this is actually writing to carrier pigeon, or there's overhead that the operating system is introducing. Looks like there's a fair amount of overhead that the operating system is introducing. Right? Because we might have expected there to be 10,000 bytes per second, but we're seeing only 1,700. Still, this is a lot of bytes per second. This is definitely as much as anybody would need. I mean, just think about it for a second, right? Like, this is the kind of, before operating systems got complicated and advanced and interesting and like actually trying to help you, these were the kinds of speeds that people were getting. Only they were order of magnitude slower because it was like the 60s and the 70s. And so like not only was there no advanced software, also the hardware was way worse. This is so slow. Like it doesn't take 70, you don't get to write only a kilobyte per second now. You can write megabytes, it feels like. So let's figure out how that is. So let's look at our next program. I'll just show you the name of the next program. You can look at the next program if you want. But let's think. What strategy would you have to make this faster? Yes? Name?
Write more than one block at a, or more than one byte at a time.
So Elton wants to write more than one byte at a time. That's an awfully good strategy. Okay, so what's your reasoning, though? What's your thought process?
If you were to write like chunks of maybe say like 8 bytes at a time,
If
would
you're,
be only doing the disk alignment or calling to the disk once, and then writing 8 bytes and then going back up, so you'd be 8 times faster.
so you'd be 8 times faster because you're calling to the disk once and then waiting for the 8 bytes to return. In terms of the way that we've discussed this earlier, this is about latency versus throughput. So what Elton believes, correctly, is that writing a unit of data that's bigger than a byte will have the same latency as writing data that is 1 byte, but it will have much higher throughput because we can do multiple bytes worth of work at once. Let's take a look at this code. Same open line. So again, we're going to go all the way out to the disk every time. How many bytes are we writing at a time? 512. Let's take a look. This is much faster. Is it 512 times faster? 847404168. It's 505 times faster. That's pretty close to 512 times faster. Question, Enrique.
Is the block size the page size?
The block size, this block size is smaller than the page size. The page size is 4096. You're asking for an experiment. Awesome. Just pick a size. What do you want it to be? Return a double? Oh, double it. Okay, we'll double it to 1024. Make W2 sync block. That's roughly twice as fast. Any other questions on sync block versus sync byte? I know it seems like a simple strategy. It is a simple strategy. It is used all the time. Always remember it. This is one of the ways that every cache works. Caches work by masking latency by doing more work than they need to. Okay, here we have a different program. This program is the same as our original W01 sync byte program. The only difference is that if you look at this line, there's something missing. Sync. Okay? So now we're not asking the operating system to go all the way out to the disk every time. Of course, you might think, if you were the operating system, would you go out to the disk? Well, what else are you going to do? The person is asking for the data to be written. Okay, so how fast is this? This is roughly 1,000 times faster than writing the data to the disk every time. What about our block code? So that's roughly 100 times faster than that. So we're now 100,000 times faster than accessing the disk. What do you think the operating system is doing? The thing that's interesting to note here is that W03 byte and W01 sync byte are making the exact same number of system calls. The exact same number of system calls. The only difference between the system calls that they make is that W01 has one extra flag in it. Okay? So I've mentioned that system calls are expensive. They are expensive. They're this expensive. The difference between W03 byte and W04 block has to do with making fewer system calls. But the operating system is clearly doing something clever. That's the reason why W01 sync byte is so much slower. Ideas, yeah, Teddy.
So it might be having like its own buffer, and that it just like flushes it every once in a while when it gets.
It might be having its own buffer, which it flushes once in a while. Uh-huh. And the back, David? Derek, sorry. Yes, Hugh.
Yeah, it might be that like the operating system maybe has like a schedule of when it wants to write to the disk, like maybe say like every 5 seconds.
So maybe the operating system has a schedule of when it wants to write to the disk, maybe once every 5 seconds. So what is it going to do with the data in between when it gets it and when it wants to write it? Sync it to main memory. Will.
If either of those things are true, would that mean that if my computer were to like shut down in between two of those writes, would I just lose some of that data that I wanted to store?
So Will's question is, if either of those things are true, which they are, is it true that when if my computer were to lose power before it shuts down, that some writes would be lost? It is true. So what we're seeing here is essentially what the operating system does with the vast majority of your primary memory. It uses that memory as a cache. This is not like the processor cache, where there's separate memory that is faster and physically different. This is just a portion of DRAM that is used as a cache in the general sense for data that's located on slower storage. The name of that cache is the buffer cache. So let me just define the word cache. So the way that we use the word cache in this class is a cache is a small amount of fast storage that's used to optimize access to a larger amount of slower storage. Okay? So that applies to the processor cache, a small amount of SRAM that's used to optimize access to a larger amount of DRAM. It's true for the buffer cache, which is a relatively, I mean, it's very large, but it is a relatively small amount of DRAM that's used to optimize access to a huge amount of memory on slower disk. Okay? When a write is made with the OSync flag, the operating system takes that data, which I'll use a different color. Not sure you can see blue, but hopefully. So it takes that data, and the system call puts that data in the buffer cache. The operating system then, at some point in the future, takes that data and puts it on the disk. So this is step 1. This is step 2, which is a block device I/O. The difference between W01 sync byte and W03 byte is that in W01 sync byte, the system call doesn't return until step 2 happens. In W03 byte, the system call returns right away. And the write to the block device happens potentially much later. Okay? This is just like the processor cache. When you write a value to memory, that write stays in the processor cache for a while. And you don't know when, at some future time, the processor decides that it will take that cache line, block, and put it into primary memory. Okay, any questions on this? Yeah. Are you David? Okay.
So say something's sitting in the buffer cache and another program wants to read that data from where it thinks it is on the disk.
So say that something is in the buffer cache and another program wants to read that data. So let's say that the other program reads it directly from disk. Then it would get the wrong data.
Some sort of thing the operating system is doing to make sure it gets the right data.
Sure is. So the operating system prevents the program from accessing the disk, right? The operating system virtualizes the disk into this abstraction that we call a file system, this collection of files. So the buffer cache, that blue dot, is associated with a particular file. If some other program tries to read that file, the operating system will satisfy that read using the buffer cache. Okay? That make sense? So the operating system is doing work to make the disk appear like it has been updated. However, the disk has not necessarily been updated. So there's a technical term for this, and I'll save that term I'll save the explanation for next time. But the buffer cache and the processor cache are both what we call coherent caches. And what that means is that the cache looks like it's up to date at all times. There's no way to go around the cache. Okay. So this is by primary memory, do I mean all storage types above SSD in the hierarchy? The term primary memory refers to DRAM. So the caches, the L1, L2, L3 caches above that are a coherent cache of DRAM. So in general, when an instruction accesses memory, it looks like it's accessing primary memory, namely DRAM, but that access is going through the other caches. How much later after a syscall is data moved from buffer cache to disk? I'm glad you asked. This is something we can actually investigate by asking the operating system to report exactly when it's moving data from primary memory to disk. So we've already seen the strace program. You probably remember the strace program. The strace program allows us to see exactly what system calls a program makes. So I can run strace 01 sync byte. And if I look at that trace, I'll see a whole bunch of writes of 1 byte of data. If I run SO3 byte, I'll see something that looks very similar. A whole bunch of writes. What I'm going to do now is I'm going to show you something that is going to look like gibberish, but I'll try and explain just enough of it to you that you'll understand the basic gist. So this is a program called blocktrace. And what blocktrace does is blocktrace makes a trace of all of the events that happen involving a disk. So I'm going to ask this program to start running. Then I'm going to run sync byte. Then I'm going to kill the blocktrace program, and I'm going to look at the results using something called block parse. So I'm paging through a bunch of stuff that happened before I started running the program. Then down here, we're going to see a lot of events that come from the program that I was running. Unfortunately, because there's so much information here, we can't really, but I'll just point this out. So this is a request, a new request from the W01 sync byte program. Sorry. Here we go. So every one of these lines represents a particular request that the block device is making. So when we saw the lines from W01 sync byte, we were seeing a small number of bytes per request. I'm going to try and repeat this. Running the version that writes 1 byte at a time, but does not write it with the sync version. Dev xvdb. Okay, get a bunch of W03 writes, kill my block trace, do the block parse. So here, I'll shrink this a little bit, which unfortunately makes it less readable, but maybe more readable like this. So what you're seeing here is a bunch of writes to the disk, but these writes involve relatively large amounts of data. So these numbers are not necessarily written in units of bytes. They're written usually in units of 512 byte blocks, I believe. So what you're seeing is that W03 byte is doing a bunch of write requests that involve a large number of bytes at a time. If we go back and do the version with the sync byte, and I'll be writing up how you can do this. So here you're seeing a very small number of bytes being written at a time. It's not writing 1 byte, though. It's writing 8. Well, 8 of this 512 byte unit. Something to note here, every one of these writes, this is a write that's happening at this offset onto the disk, like roughly 5.45 billion. Sorry, whatever it is, doesn't matter. It's like 54552.152. We're going to see that offset written many, many times by the W01 sync byte program. It's like the same offset is being overwritten again and again and again. In fact, I'm not convinced that if I went to the end of this, okay, here's a different one, 545.52160. But you see that offset just being overwritten again and again and again in the sync byte version. In the byte version, you're not going to see that. You're going to see a different offset every time. (44960), 45216. This is a completion record of the earlier one. 472, 728, 984. Okay? So again, this is relatively complicated information. It is scary information. But you can read manual pages and really figure out what this is doing. And if you ever become like an actual low-level systems engineer, this kind of debugging information is just like treasure. It can really help you understand what is wrong with your program. If, for example, somebody decided that your program should run much slower than theirs, so they hacked in behind your back and added an ODirect flag or an OSync flag so that your writes were slow, you could figure it out from this.
Why is it writing a different number of bytes each time?
So this is a great question. So how big is a cache block? Do you guys remember when we talked about the processor cache? We talked about it in the area of alignment. Do you remember? Yeah, 64 bytes, right. Juan? So, thank you. A write to memory from the cache, when the cache writes to memory, it always writes to memory in aligned units of 64 bytes at a time. So that means if you write the bytes in a cache line from beginning to end, 1, 2, 3, 4, 5, 6, 7, all the way up to 64, the cache will collect all of those writes into one unit and then make one write of 64 bytes down to primary memory. This property of aligned movements of units of storage is true of every kind of storage that we've got. The unit of storage that a flash drive has is, it looks to me like 4,096 bytes. It looks that way because the number that we saw on W01 was 8. It was writing 8 512-byte units at a time, every time. So what that meant is that what the operating system had to do when it was asked to write 1 byte, 1 byte, 1 byte, 1 byte, is essentially it would construct 4,096 bytes in memory, write the 1 byte at the correct place, ask the disk to write 4,096 bytes, wait for the response, return. Get asked to write the next byte. It would collect that in memory, write the full 4,096 bytes out to memory, wait for the response. Okay? So that's why that offset wasn't changing. Because of the way the disk works, every write of 1 byte gets expanded into a write of 4,096 bytes. Here, though, thanks to the buffer cache, the operating system is not writing the bytes one at a time. It's not performing one write of a full block out to the disk for every write system call. Instead, the cache is collecting 4,096 of those writes, at least. In fact, sometimes we can see that it's collecting far more than that, right? This line here, plus 1024, that is writing 512 kilobytes of memory in one unit. So the buffer cache in memory has just saved up 512 kilobytes worth of data before the operating system was like, it looks like these writes are done, and shipped them all out at once. Okay? Does that make sense? This is one of the key ways that the operating system speeds up writes. Okay, As always, I've probably lost this forever, so good luck asking a question. Last program for the day. So this program, how many bytes does it write at a time? 1. It writes 1 byte at a time. 1. Right? That's the way the fwrite system call works. Fwrite is like the standard I/O, the standard I/O library's version of write. Let's see how fast fwrite byte is, this standard I/O byte version is, compared to the regular by byte version. So there's standard I/O, being asked to write 1 byte at a time. There's making 1 write system call at a time. So what's the performance difference? 30. Looks like it's about 30. Standard I/O is real good. You're going to beat it, but it's very good. Okay, any idea what standard I/O is doing to turn writing 1 byte at a time 30 times faster? There are a lot of people who have ideas, but rather than tell me, I want you to tell me what to do to find out. How can I find out? Yeah, what's your name? Matt. strace. Why don't we check what system calls this byte at a time program is running? How many bytes is the standard I/O version writing at a time? The standard I/O version is writing 4,096 bytes at a time. So it's making a factor of 4,096 fewer system calls, and that is why it's running roughly 30 times faster. It's not running 4,096 times faster because there's a fair amount of infrastructure within the library to support this 4,096 call. So your job is to do this and more. Okay, cool. Next time, more.